We'll be looking at routing, in this case multi-stop routing, where each shipment can have a different origin and destination. And we're going to be looking at combining multiple shipments into a route based on minimizing their total logistics cost. This is a tactical solution as opposed to the traditional vehicle routing where we're just trying to minimize the distance and number of vehicles required. First example is similar to the example we saw before for 3 shipments. And we have 6 different origin and destination locations. We can estimate the actual road distance between these locations and then define a truck structure. And we're going to be defining the weight and cube capacities, and then the transport rate is going to be $2 per mile. We can then add an annual demand, since we'll be doing total logistics cost together with different dollar per ton valuations, alpha values and a H value, and beginning and ending points for the 3 shipments, and then define the distances of the 3 shipments and use the structure display to determine those 3 values. And then we can plot all 3 independent shipments using the same route plotting that we had discussed in the previous video. We can then use the min cost insert, looking at first just the distance traveled and trying to minimize the distance traveled. We can use the insert improve. And we end up then with a multi-shipment route where each has different origin and destination points. This is the corresponding labels indicating the pickup and drop-off points for the shipments. And then when we have multiple shipments with different origin and destination, as we look at the route, each segment of the route can have a different mix of loads. The function in MATLAB route to load mix allows us to determine what that is. And for this particular example, there are 2 load mixes. First, we have shipments 1 and 2 on board, and then shipments 2 and 3. So not all 3 shipments are on board at the same time. In that case, and for this example, we have a single load mix where we have a segment where we have all 3 shipments on board. The reason for looking at the load mix is to be able to determine what is the binding constraint relative to vehicle capacity. And to do the determination, we need to look at each of the individual road mixes to determine which set of shipments is going to give rise relative to the quantity that we want to ship to the most capacitated segment. And from that, we then have to, if it exceeds whatever the available capacity is, then we need to reduce the amount that can be shipped for all the routes. Next, to be able to do the total logistics cost calculation, I want to compare it to less than truckload. So I'm going to define a PPI for LTL using just the empty array, which will give me the default LTL PPI for 2004. I could then call the min TLC function and then display the result. The min TLC function returns as a third output argument whether or not the shipment is LTL or not. So I can include that as part of the information added to the shipment structure and then display the results. Here overall, all 3 shipments have a combined total logistics cost of over $21,000, and they're all shipped using truckload as opposed to LTL. To be able to then combine them, I can define a function handle using the min TLC function. And I'm going to add 2 additional input arguments. First the D matrix and then the route vector, and make that my variable argument in my function handle. And then I can pass that to the insert improve procedure. And I'm going to start with the second of the load mixes corresponding to shipments 2 and 3. So if I start forming my routes with those 2, and then take the resulting route, apply the min TLC function, I get corresponding quantities required. And if I look into the route, I can see that, yes, it is shipments 2 and 3 that are in the route. I can also then look at the shipment frequency, and I see 0.0672 is the frequency for both shipments. Since they're in the same route and the assumption is that they're going to be repeatedly shipped together, they are required to have the same frequency. That is by definition. If we add then shipment number 1 to the consolidated route, we can use directly the min cost insert procedure, where we add shipment number 1 as a single shipment route to the route from shipments 2 and 3. When we do that, we get a single route that has all 3 shipments, and then we can do a similar calculation. And for this, we can see that for all 3 on board, the frequency has been reduced from 0.067 to 0.058. And also the quantities for shipments number 2, it was shipping over 13 tons. Now that's been reduced to under 12 tons. So there's been a reduction by adding shipment number 1. We're having less of both shipments 2 and 3 that we can ship, and our frequency has increased and our interval has decreased. Looking at the load mix, we have the same load mix 1 and 2 and then 2 and 3. What is happening is that inside of the min TLC function, it's doing the calculations that are also displayed within this cell. So I'd like to step through the different steps, and everything that is happening within this cell is actually also occurring inside of the min TLC function whenever it is passed a route vector, and it needs to then determine what is the feasible quantity that can be shipped, taking into account the maximum payload capabilities of the truck as defined in the truck structure. So what happens is it first starts off and looks at all of the shipments as a single aggregate shipment, adds distance information, and then you end up with this result. So this is everything shipped as a single shipment. This is just the overall distance, and the route total cost function given this route vector uses the distance matrix to determine this distance value of 848. If we had no vehicle capacity constraints, then we can use the analytical formula for truckload and determine that overall we'd like to ship 73 tons. We could then break it down into what would be shipped for the 3 different shipments, and this is the then allocated quantities that would be shipped for shipments 1, 2, and 3. But if we compare this to what was actually returned by the min TLC function, you can see that that's a reduced value that was returned. So that's obviously not feasible, and the reason is that there are capacity constraints. So the way that the capacity constraints can be determined is to look at, for each load mix, the ratio of the maximum payload for that particular load mix, in this case load mix I, relative to the sum of what is the total quantity that you'd like to ship for that load mix. So the ratio of what's feasible payload relative to what the desired payload is, that ratio is then compared to K, which we start off with K equal 1, and then we look and we can take the minimum of whatever the current K is to the new calculation. If the new is smaller, then it becomes the new K value, and that is then repeated for all the different load mixes. And when we finish, we end up with the same result returned by the min TLC function. So this is what's happening inside of the min TLC function. Finally, to be able to look at each of the load mixes with respect to the weight and cube, we can use the cell function that we used previously to compare different routes for the vehicle routing, and we can do the same thing for the load mixes, where here we're using the cell array of load mixes as opposed to the route cell array. And for that, then we can first calculate weight and then cube and then report the results. And we can see that the load mix number 1, consisting of shipments 1 and 2, is the binding load mix, because that load mix reaches the cube capacity of 2750 for the route. The next example is going to be using the same 30 shipment North Carolina example that we saw with the vehicle routing. And in this case, instead of adding a depot, we're going to be using the original data. First, I'm going to close all my currently open figures and clear out all of the variables. Load the shipment data. This is what's put into the workspace. Define default 2004 trucking rate of $2 per mile and our standard truck capacities. And then I'm going to be creating my shipment structure along with the distance calculation. And the distance calculation is determined like we've done previously using the beginning and ending point locations. Here I'm using my default LTL for 2004 PPI value. And then with this, I can then use the min TLC function just with 3 input arguments to determine the optimal independent shipment quantities by minimizing the total logistics cost for each. I get the same 3 outputs. I can then add those 3 outputs to my shipment structure along with the maximum payload. And then all of that I can report. So the initial part for each shipment is the original information. And then starting here with the total logistics cost, it gives the minimum total logistics cost for that shipment shipped as an independent shipment, the corresponding size, the shipment interval, and then whether or not the shipment is shipped as LTL. Here we have 4 cases where the shipment is shipped as LTL, and then here is the underlying max payload for that shipment. We can then plot the shipments. If we zoom in, we can see that the LTL are blue and then the truckload are in green, and a lot of the shipments overlap, so there are potential benefits associated with being able to consolidate the shipments. For doing the consolidation, we can define a min TLC handle, where here we have the 4th and 5th input arguments. This is the default 2004 LTL value. I can also define a handle to be able to do the plotting as I do the route formation. And then I can calculate the pairwise savings. And then when I apply the savings and 2-opt improvement, press any key and I can see the results of the savings followed by the improvement steps. And when I finish, the one thing to note is that we have a series of consolidated routes formed, but we do have some locations that are not included. And what they correspond to are locations for shipments that were not included in any of the consolidated routes. The reason being is that there was no positive savings associated with combining that shipment with any of the other shipments. So no consolidated route of more than one shipment was created by the savings procedure. And the savings procedure doesn't do that if there are no non-negative, or in this case strictly positive, savings associated with combining the shipments. So to handle the case of single shipment routes, there's a function shipment to route that goes in and adds to a route a series of, in this case, several different independent shipment routes so that they're added. So we have a route cell array that includes all of the shipments. And when we do that, you can see now that in addition to the 4 routes that were created, each of those are given different markers so they can be identified. Also, the independent shipments carry over to this plot. And you can see here that for shipment number 4, it's not added to any route, so it's better that this remain as an independent shipment. Reason being is that the additional cost travel to the origin of shipment number 4, and then after delivering it, adding it, it's not compatible with adding it to any of the existing routes. That additional cost made it not beneficial, so it was better to keep those as independent shipments. Likewise, you can see there are several other shipments, and this shipment remains as an LTL shipment. To look at the percentage overall, everything shipped as independent relative to the consolidated, including the independents, we have a little under 12% reduction. To make it a little bit more comparable, we can eliminate the shipments that remained as independent shipments and focus on just the ones that were added into a multi-shipment route. And looking in that case, we see there's a little over an 18% reduction. That's in line with what we would typically see of 15 to 20% as the benefits associated with consolidating multiple shipments into a route. The next example is to look at a case where, unlike the previous case where we're looking at a single total logistics cost minimization for all of the shipments, we may have a case where each shipment is operated and owned by separate entities. So there's no single entity that can capture all of the total logistics cost savings. So it may make sense to, for one shipment to do something that, even if overall the total logistics cost is not as high, individually a single shipment might benefit more depending on how the different costs are allocated. So in that type of distributed decision-making environment, the question of how to best allocate the cost to each shipment when they're consolidated becomes an issue. And as talked about in class, the Shapley value is one means of doing that allocation. So for the example on the slide, we can calculate and create shipment structures to find a transport cost. In this case, it's going to be 1, so that the cost corresponds to the distance of the shipment. And then we define N as the number of shipments. We can then first look at what would be the charges for all 3 shipped independently. That's just equal to the distance. And then in this cell, it goes through and does an exhaustive calculation of all of the different permutations corresponding to the different ways of looking at each shipment as it's added to a route. So here each row label indicates the sequence at which shipments are added, and then the cost information for each shipment corresponds to what is the additional cost for that shipment when it's added to the existing route. So it's always the most costly to be the first shipment added, and then later in the sequence it becomes progressively less costly. And in the case of at least shipment number 1, there are these 2 cases where there's 0 cost associated with adding it. And if you look at the figure, it's because shipment number 1 is between shipment numbers 2 and 3. So when 2 and 3 are already in the route, there's no additional cost for shipment number 1 to be added. Instead of the Shapley, other potential ways of dividing the cost would be, one would be an equal charge allocation. And looking at that, we get the total cost of $430 for the consolidated route, just split equally along with this percentage reduction. We can also look at what would be the savings, and if we added up the individual independent shipment charges, we get $825, and then consolidated is $430. So that difference of $395, we could allocate it equally and subtract $131 from each of the independent shipment charges, and we get then this result. And looking at this as the percent reduction, you can see that you get different results than you did for the equal allocation. And in particular, shipment number 1, its percentage of cost reduction is less in this case. So it doesn't do as well with the equal savings allocation. Whereas shipment number 2 is doing better in this case, and shipment number 3 stays the same. Looking at the Shapley, here you can see that now shipment number 1 does the best with this allocation in terms of getting the largest percent reduction in cost. And looking at the figure, it really can be explained as being, I think, the most fair result compared to the other 2, because shipment number 1 being in the middle is likely to have the least amount of additional cost required, when it's added to a shipment compared to 2 and 3. And in this allocation also, shipment number 3, which is the one that has the largest additional cost whenever it's added because it's further away from the other two shipments, has the least amount of reduction. So the Chapley means of allocation is capturing those differences. Because of computational infeasibility of being able to look at all permutations of, and all different subsets of routes, as a result of that, you can use an approximation. One simple one is a pairwise approximate Chapley allocation. And we can do that by first calculating the pairwise savings and then applying the approximation formula. And when we do that, we get exactly the same results as the Chapley calculation. So there's no difference between the approximation. In this case, we can then take all of our different allocation approaches and compare the different results as one summary table. The last thing to talk about is if we add a fourth shipment, we can actually show that there'll be a slight difference between the exact and the approximate Chapley allocation. And I'm going to do that by first adding a fourth shipment. And now n is equal to 4 as opposed to 3. Then I can go back up here and then just repeat the calculations in each of these cells. Here it takes a little while for all of the different possible routes for the exact Chapley to be calculated. For each different sequence, the insert improve procedure needs to be determined. And these are the overall results. For that, then we can recalculate the equal charge, equal savings, and then the exact. The exact is just the average of each column of the C matrix, the pairwise approximation, and then comparing the results. Here you can see that there is a difference between the approximation and the exact solution. And you would expect as the number of shipments increases beyond 4 that there'd be greater and greater differences between doing the approximation and the exact. But given that as the number of shipments increases, it becomes less and less feasible to do the exact calculation, the pairwise at least gives us a lot of the same benefits that Chapley does. And that's a computationally feasible way of actually implementing this type of allocation procedure.